Good afternoon, and sorry to interrupt everybody's lunches, but we've got a really great selection of panelists for this next discussion on next-generation battery technologies. We're going to be talking with a few companies in the solid-state and sodium-ion space. My name is Andy Leach, so thank you very much for joining this session. Battery demand will grow almost 4 times by 2035 from 2025 levels, according to Bloomberg NEF. Most of this growth is expected to come in lithium-ion. However, new technologies such as solid-state and sodium-ion batteries are reaching maturity. The large market size of 1.8 terawatt-hours of demand expected in 2026 from transport and storage means that if emerging technologies take only a small market share, this is a really, really big opportunity. BNEF's expectations for sodium-ion batteries demand by 2030 is 100 gigawatt-hours. This is half of all of the transport and storage demand from only 2020. And for solid-state, BNEF expects semi-solid and solid-state batteries to reach 180 gigawatt-hours by 2030, almost twice that of sodium-ion. So we've got some speakers here. We've got Tim Holme from QuantumScape, the Chief Technology Officer. We've got Dr. Siyu Huang from Factorial Energy, CEO. Landon Mossberg from Peak Energy, CEO, and Dr. Sven Ji Dao, CEO of HYSA. So I want to sort of understand from each of you, what is the current state of play? So we've been talking about solid-state and sodium-ion for more than a decade, but the tone feels different. From where you are, what has changed in the last couple of years that means these next-generation technologies are commercially credible rather than just promising? So Sven, you're already demonstrating high energy density and power density and strong safety performance. Your thermal propagation tests, I mean, you showed me yesterday in this room, actually, how impressive those were. So how close are these to real-world commercial deployments in EVs, aviation, rather than just lab benchmarks?
Thank you. First of all, and thank you very much, and I really appreciate this opportunity to speak here and introduce our technology here. And before I answer your question, please allow me to give a short introduction about this technology, where it comes from, and basically what we have done in the past couple of years. Basically, this technology has been developed from Chinese Academy of Sciences, from the Research Institute, and since 2017, and this technology has been used to power the landers at the bottom of marine trenches. It powered the landers, they're working continuously for 26 days. So in the past, it was mainly underwater application, and the reason is that, for solid-state battery, and we know the interface is a big issue. When you put it under the water, and then the water pressure will naturally to make it better. Yeah. So this is very, very, very important, I say, advantage to do it first, start from underwater. And since 2022, and basically we founded this company and to commercialize it. It's like the spin-off, pretty much with like others, spin-off from the Research Institute. And in the past couple of years, what we have done is that we transformed this advanced technology into a commercial, I would call it a proto-product. We are working closely with the global OEMs in terms of the real applications for different ones. For example, I think coming back to your question and how close it is to the commercialization, I would say now it's more or less in the coming 2-3 years, and then we should be able to see the speeding up. The reason is that we have done, for example, for the drones, just make one example, and we were working with one heavy load drone for industry application, and the lifting weight was 25 to 30 kilograms. With conventional batteries, and they can fly only 18 to 20 minutes. And last year, and when we did this demo and tried with our batteries with high energy density as well as high power density, and it reaches, let's say, 1 hour. Yeah. So this kind of lift is huge, and our customers, they are quite impressed as well. At the same time, what we are pretty, let's say, proud of as well. Just now, Andy mentioned that for the thermal propagation, we were working closely with the eVTOL OEMs, and our battery with high energy density, like 320, even to 340, and with large format, up to 50 ampere watt hour, and it's modular. When we trigger 20% of this summer runway, because they are testing the limits, and all the adjacent cells, and they kept it intact, even there is no voltage drop. And this is in the pouch cell, and also I would say this is without any, let's say, the pack modular designing, special designing, we can pass this test. So basically, we can demonstrate and prove the high safety, high performance on a same cell with large capacity. And this brings my confidence that in the coming 2 to 3 years, and we should be able to see the picking up in terms of commercialization.
That's great. I look forward to seeing how the next couple of years play out. But yeah, the sort of applications you're already demonstrating, I mean, sending a sort of a robot down to the bottom of the sea is particularly interesting and a fun example. Tim, QuantumScape is now delivering samples to A and B samples to automotive partners. And from your perspective, what do OEMs now believe about solid state that it maybe didn't a few years ago? Like, what is happening at the minute? What are you guys doing right now that you're finding is particularly promising?
Yeah. So we've been working in solid state technology for about 15 years. The industry has been working for even longer than that. So Gates's law is people overestimate the amount of progress they'll make in a year, but underestimate the amount of progress they'll make in a decade. And so I think what's changed is a lot of accumulated learnings throughout the industry and in our company, so that we've now been through a lot of learning cycles. As you said, we've delivered automotive A samples and B samples to our partners. In last year's International Auto Show in Munich, we did a demonstration with Ducati of a racing motorcycle with our technology inside it. And the way that Volkswagen phrased it is from lab to commercialization. And so it's through milestones like this of real-world demonstrations. I think CEO will probably tell you about her real-world demonstrations. Through the ecosystem achieving progress like this, I think it becomes really real. And it's not anymore the technology that people promise in the future someday, but it's coming. And you started this talk with an introduction of solid-state batteries being 100 gigawatt hours. That kind of scale is quite vast. And so I think that's what's been changing, is just accumulation of real-world learnings and starting to deliver products for real-world demos. Yeah,
and I think, as I said in the intro, even now small parts of the market share can be absolutely vast, absolute values of gigawatt hours. And yeah, great that you talked about the Munich Auto Show, because that leads straight into my question to see you. And I think you may even have a prop, but I'll let you get to that. But Factorial has moved from prototype cells to real-world demonstrations, including a 1,200+ kilometer journey on a single charge. Yeah, what do these demonstrations signal to automakers about risk and trust, and how ready you and all other solid-state companies are for coming to market?
Yeah, thank you, Andy and Tim, for sharing this teaser here. CEO, I'm the founder and CEO of Factorial. A quick background about us. We actually founded out Cornell. I got my PhD in chemistry from Cornell and built my first company in the battery material manufacturing space. We sold the company, and this is the second startup. We have been building a little bit less than 15 years, but more than 10 years right now as well. And our first investors were Hyundai and Kia. And Mercedes Stellantis, they led the 200 million round in the company a few years ago. So that builds the core part of our partnership right now. And I would say, to answer your question, Andy, like where the status of the world right now, I think solid state is already moved beyond the lab scale. Like we actually delivered this. There was the world's first 100 amp hour solid state battery with the lithium metal with high energy density battery. This is 390 watt-hour per kilogram in terms of energy density, compared with traditional lithium-ion battery, which is roughly about 260 to 300 for automotive batteries right now. This is about at least 30% and potentially can get to 50, 80% higher energy density compared with traditional lithium-ion batteries. And we also are very, very dedicated to build a process that's highly compatible with traditional lithium-ion batteries. So this is more than 80% compatible with today's lithium-ion battery manufacturing process, which means all this $1 trillion investment into the space and can be reutilized and scale up very quickly. And as Andy said, that actually in the same auto show last year, in the Munich Auto Show, I think it was exciting to see definitely the vehicle from Ducati there. And at the same time, we also announced with Mercedes a record drive of the EQS. You may have heard about EQS in the market. It's been around for the last 3 years in the US market. It's a top-of-the-line flagship vehicle for Mercedes. We actually started in February when we built the first vehicle. And they initially challenged us to drive for 1,000 kilometers because their status quo is 800 kilometer with their CATL battery inside. And they challenged us to go further. And in August, when we did deliver that record drive, we initially target to go from Stuttgart all the way to Copenhagen. And actually, we didn't stop in Copenhagen because we still have so many miles left. And we drove all the way to Malmö, Sweden. That completes to 1,205 kilometers. And we still have 137 left. It's not a downhill. It's all flat in a public drive. And we're really glad that we're making it. And moving forward, we do see there's an exciting path for this technology to be commercialized. And we're targeting as early as 27, 28 to have the first commercial deployment.
And maybe when you got to Malmö, you kind of run out of roads. You've driven all the way through Germany, all the way through Denmark, and now you get to the end of the road with miles still left on the clock. No, that's great, and it is, as I say, really impressive to see where you are now and the progress that's been made. Moving to Peak Energy and sort of shifting gear a little bit with respect to technology. So, Landon, you guys are doing sodium-ion technology and focusing more on not making the cells yourself, but making systems. And thinking everything around the cell. How mature is sodium-ion today compared to lithium-ion? And of course, I assume you're focusing more on the ESS industry, so
yep.
Trying to displace the incumbent, but in a different side of application maybe to the other panelists.
Yeah, so I'm in rarefied air up here. I think I'm the only non-doctor, and I'm also the only non-battery company. We're more of an energy company, but we're an energy company with storage at the center of what we do. Our first product is a sodium-ion grid-scale ESS, so it's a a little over 3 megawatt hour, 3 megawatt 4-hour energy storage system. I think like 100,000 pound, 20-foot container of batteries. It's about 8,000 large format prismatic sodium-ion cells in our first system. So I mean, to answer your question about scale. The nice thing about sodium-ion, similar to what you mentioned, it's pretty much compatible with existing LFP infrastructure on the cell level. So you go to a cell fab. In fact, most of the sodium-ion cells that are produced today are produced on LFP lines. There are some tweaks to the process. Usually sort of resize a couple steps in the process to streamline it and make it easy to flow through. But even if you don't do that, you're just producing a little bit less efficiently on the same line. So that's why it's come up so quickly. On the raw material, or on the bill of materials, pretty much everything but the active material is the same. So anode and cathode are different, but you're using aluminum on both sides of the current collectors, but everything else inside the cell is shared. I guess a little bit of tweaks in the electrolyte as well. And because of that, you've seen a massive, and almost it feels like overnight. There was sodium-ion was kind of a cool idea, and then suddenly there's gigawatt hours of capacity out of China. And that's how we're shipping. We shipped our first system over the summer. That's been cycling now for a few months, and then customer deliveries are starting in April. We're scaling up. We'll deliver several hundred systems next year. So it's at scale, and China's moving, believe it or not, China's moving faster than we are. So it's happening quick.
Yeah, there's maybe a theme in the battery world that there are companies over in China and plants there are moving pretty quickly. But yeah, I think that sort of sets the scene as to where we are. As I said in my intro, and pleased that you guys agree, but we're at a point where these technologies are proving themselves at the sort of in commercial applications, and hopefully at an inflection of making really, really big impacts. So to think about some of the maybe hurdles that we're going to come to sort of overcome to make sure that we realize that potential. In the next 2 or 3 years, what do we think are the sort of hardest problems to solve? Not theoretical ones, but in practice to get these technologies to those 100, 180 gigawatt hour numbers that I sort of suggested are our outlook. So Landon, on sodium ion, some of the challenges are maybe, we were talking just before as well about, the performance is really, really good. But there are maybe things around SEI stability. How confident are you that these are challenges that are engineering problems are not fundamental limits? And how quickly do you think you can scale to sort of meet my expectations of what I'm telling my clients?
Sure. Yeah, I mean, I would, I think 100, it sounds aggressive. I think it's going to be undershot depending on what you see on the LFP side. What makes sodium-ion special, at least in our application, is that it enables you to build an ESS system that's fully passively cooled. So if you don't know anything about it, like traditional, like a Tesla Megapack or a CATL Tenor system, they're like giant container-sized refrigerators that sit out in the desert and have to operate for 20 years, and they have very high uptime reliability requirements, all of that stuff. The things that break that also cause fires and stuff like that, it's almost always related to the thermal management system. Those also cost a lot of money in terms of power usage and complexity and maintenance and all of that stuff. So what we've done with sodium ion, because it can operate at a much wider temperature range, and we've tweaked the cell to go even wider, is taken all of that complexity out. We have a fully passively cooled energy storage system, and that ends up netting you about a $75 per kilowatt hour net present value benefit on a TCO basis.
Just quickly, what temperature do you think you guys can go up to at the minute?
Right now, we're very comfortable at 60 degrees Celsius max. It isn't like you can see LFP push up there, but we are happy to be at an average of 45 degrees Celsius over the life of the battery, which compares, and we have lower degradation at that level than LFP does, typically around 25. And then you have to do a lot of work, which is where we've spent a ton of engineering time too at the system to make sure you have like a consistent temperature across all 8,000 cells in your system and all this other stuff. So it's a super non-trivial problem to solve, and it requires a lot of system level engineering as well as cell level engineering. But once you do it, you have a fundamentally safer, cheaper, more reliable system, which makes the IRR for a project developer, if you're developing a utility scale energy product, substantially higher. We're about 50% better return on investment for grid scale project developers already today at our current techno-economics. But when you look at like data center applications where reliability is an absolute premium, the amount of overbuild you have to do on LFP is substantially higher because those systems, they need more downtime than we do. So we think it's like massively competitive now, and it's getting more competitive for these future applications that are driving the space more and more.
Sure, thank you very much. Moving back to you, Tim, thinking about QuantumScape and where you guys are going, some of the really impressive innovation that I've seen from you guys is around the ceramic separator that you have, and in solid-state batteries, the separator is often one of the key pieces of technology. You highlighted the Cobra process that we spoke about in advance. So if you could just sort of maybe sort of bring the room up to speed on this, but also what is the challenge for this and for QuantumScape in general? Is it scaling the technology, scaling the manufacturing of the materials at gigawatt hour? Is it about cost or yield, or is it just time and you have sort of what you need, you just need to build that out?
Yeah. So I think conventional wisdom of solid state is the main challenges are things like pressure. Can you operate at low pressure? We've demonstrated that our batteries don't need to operate at pressure. And I think a lot of that comes back to the separator that you mentioned. So it enables us to operate at low pressure. So that, I think, is one of the major challenges that has been solved. The major challenge that we have going forward is scaling, as you discussed. And the key material in our battery is the ceramic. If you are a potter, you make ceramics in a very slow process. A key step involves putting your pottery in an oven for days at a time. That does not scale to battery production. We knew that, we recognized that, so we have reinvented the ceramic process. It's pretty remarkable considering that ceramics have been with humans for thousands of years. Like, go to a museum, you'll see these Neanderthals made these pots or something, right? Nevertheless, I think we had a major breakthrough in the science and engineering of ceramics to be able to make that key step much faster. We did this in 2 stages that we rolled out last year and this year. You referred to Cobra, which is what we call our current iteration, that has shrunk the key step down from hours to minutes, from like many hours to several minutes. That's really key in enabling scalability. And so that, I think, was an unlock for our technology that's going to allow us to address these gigawatt hours, hundreds of gigawatt hours, terawatt hours that you were talking about that the battery market needs.
Yeah, and also with respect to sort of the way that you're sort of coming to market, you're looking to license this technology rather than manufacture yourself, right?
That's right. Yeah. being based in Silicon Valley, I remember our first board meeting at which John Doerr came and said, California is a terrible place to manufacture anything. We'll see if he's right or not about that, but if you look at the cost of labor and land and electricity and regulation and so forth, it is challenging to manufacture in California. Really, the core DNA of our company is technology innovation. And so we want to lean into that and keep developing next generations of technology that solve our customers' problems, whether that's increased performance, reduced cost, better scalability. So we're going to be rolling out subsequent generations of our technology over time and licensing that to partners. So our biggest publicly announced licensees, one is PowerCo, which is Volkswagen's wholly owned battery subsidiary that we're working with as in a very close collaborative relationship to put our technology into the gigafactories that they're installing in Germany, Spain, and Canada. We've also announced partnerships in Japan and in the US with really world-class companies like Murata and Corning.
Thank you very much. There's a lot of pulling the supply chain together to make sure that, as I say, we can overcome the challenge of getting to the scale that automotive requires. Steve, Factorial also pursuing sort of a drop-in approach, trying to leverage existing manufacturing capacity. This is both. Does this meaningfully reduce the scaling risk? Does this mean that you can move more quickly over the next couple of years? And then are there any other barriers to going fast? So I know that you're using lithium metal as your anode, and sometimes producing this at scale can be a challenge as well.
I would say I would see the challenge mainly coming in three folds. Number one is automotive market is really difficult right now. I would say everybody has to admit, like EV market in the US is pretty much dead. And I think that's why we think like finding an alternative path and also finding the market that's much shorter cycle life and much shorter adoption cycle is going to be very important for us. So that's why we recently announced a partnership with a drone maker in North America to deliver a high energy density drone. Because for passenger vehicles, battery is nice to have with higher energy density, longer range, but drone is a must to have, right? That's like it completely changed the game on a battlefield or in a cruising situation. So I would say that's one market that we definitely think is going to be an immediate field that we're working in, and we have some exciting news coming up as well. Number two, I think is really to work on the progression of the partnership. I mean, we have recently signed MOUs with some of the major like supercar company and some of this leading commercial partners we're having. And I think continue expanding that. Like after we had the first vehicle last year with Mercedes, we're actually launching another fleet this year with Stellantis. It's going to be led by the Dodge Charger Daytona as one of the leading STLA Large platform under the Stellantis platform. So that's not only just one Dodge, but also with Jeep, Chrysler, and up to 2 million vehicles a year as part of the annual demand. That's potentially going to be the next stage we're moving in before the commercialization. And last but not least is really on the supply chain side. I totally echo with Tim and the supply chain is really the key. That's where the innovation and that's where the security coming from. We recently, last December, actually 1 month ago, we just announced a partnership with POSCO, which is the top cathode maker in the world. And they also do anode, they do all of this different type of materials. And the year before, we also had this partnership with LG Chem. So the beauty for Factorial's process is that we're highly compatible with lithium-ion, not only just on the process equipment side, but also on the material side, from cathode to separator and various other components. So we're very conducive to the traditional lithium-ion process. So that's why we think like we've already achieved more than 80% yield in our factory in South Korea. So we do have a wholly owned subsidiary over there, and we're doing mass production for some of these high-spec, like high-performance customers already. So that's something like we're very excited to see the supply chain, despite of all the discombobulated world right now, will stay stable for our partnership and coalition.
Yeah, hopefully we can have some stability so that everyone can continue to make progress.
Right.
And great to see, the relationships that you're building and developing in the supply chain to ensure, both the material side and then manufacturing and on the customer side. Sven, we spoke about you spoke about the sort of the challenge of the scale and some of the applications that you're getting into already. In China, maybe the EV market is growing a bit more strongly than it is here in the US, and Europe is somewhere in between. But is that a great opportunity, or is also that a challenge because the market there is very congested with lots of manufacturers and very, very low prices?
Oh, I would say that this is basically both parts combined. Yeah. First, let's say the EV market in China is growing so fast, and also let's say the Chinese automakers, as well as the customers, they are more open to the new technology. And I mean, the barrier to test new technology and also to get it approved, and this is pretty low. You can do it pretty fast. On the other hand, that the cost, because the cost is always the major topic, not only for the majority, let's say the large players in these sectors, for example, like CATL and also EVE and SWOT, etc., but as well as for the young companies. Yeah. For example, like in the semi-solid state batteries, like the Qingdao and the Weilian, and they are also facing pretty similar, let's say, situation. Because when you have new technology, but your price is higher than the incumbent one, and then the people will be thinking about, let's say, what's, let's say, additional benefits. Therefore, the most, let's say, difficult part for, let's say, the technology like us, I would say, is that how could you, let's say, prove your performance could adding additional value to the end users. Safety is something they see it, for sure. This is a must-have. And everybody regards this is definitely, especially for me, safety is, if not the only thing, but it is one of the most important things we should not compromise. Anyone should not compromise. On the other hand, is that about what's the performance. And for example, just taking one example, different applications, they have different, let's say, requirements for the performance. And when we started this company, and it was using for the underwater powering, let's say, the AUVs, etc., and also the landers, the power density does not need that high, because you don't need, let's say, that kind of high power. But when we move to the EVs and start working with the top OEMs, and then the first question is that about the charging speed, at least 3C. And you know, I think the team and also you know that in the solid-state battery territory, the interfacial impedance, I mean the resistance of the interface between the cathode, anode, and the electrolytes, and that's extremely high. How to address this point? And therefore, we have to work a lot on our, let's say, material and electrolyte side. And finally, we could, let's say, boost the charging rate to more than 3C. And also, we could discharge ourselves.
Just quickly, I want to say, for those that aren't battery scientists in the room, 3C is a 20-minute full charge.
Oh, yeah, sorry. Yeah. And also, let's say, for the discharging rate, it means that for within, let's say, 6 minutes, and it could get, let's say, fully discharged. And this fits the eVTOL application pretty well. Yeah. I think this is something that we need to find the way along, our pathway along all these challenges. And before, let's say, we could really bring a product in the market, and how could it combine all these advantages people are expecting to a real product. Yeah.
So both an opportunity and a challenge, having a growing but very competitive market in China. So looking ahead to where the best opportunities are, the next 2-3 years, moving to the late 2020s, where do we see the biggest commercial upsides for these next generation technologies? Are there any markets where we're underestimating the opportunity for new technologies? So, CU, if I can start with you, Factorial is working with multiple global OEMs and targeting high-spec applications first. I assume these will come in premium technologies first, premium vehicles first. But do you also see that this decade we can have solid-state batteries in mass-market vehicles, or is that something for the future?
Yeah, absolutely. As I said, we had our first vehicle last year, and we have our first fleet this year. We're targeting as early as 27, 28 for the first commercial deployment. And it's likely going to be in a vehicle, and it could also be in a drone and some other applications. We do see there are a lot of emerging markets. Drone is definitely a very hot one out there in the market. You know, right now, US, more than 85% of the drone batteries are coming from China. And even just in Ukraine, there are like 4 million drones every year, right? And that's a huge market that's growing every year too. And however, like China recently launched this export control restrictions for any batteries above 300 watt per kilogram battery for export control. So there's a lot of challenges. Of course, the policy can come on and off, right? But that's going to be the trend in the next few years. And right after that was announced, the U.S. government sent a big delegation to us and say we need your battery, because there are very few battery makers in the U.S. can supply right now. So I truly believe there are going to be more than one winner in this space, as Tim just mentioned. And I do think that Joy's national security sits right in the front and center for our priority, our nation's priority, and also Factorial's priority as our next generation leader for batteries. And beyond that, I do see robotics is another very interesting area. And together with AI data center, right, that's another very interesting area for energy storage. And to my surprise, data center, I thought there were a lot of demands on LFP battery and some of the large size utility scale batteries, but they do care about the pulse discharge, the power capabilities in the data center. Humanoid is another function that in the future, now it looks very small miniature market. But in China, actually, there was the second largest automaker in China in doing EV called XPeng. I don't know if you heard about that podcast recently. He said that we know XPeng is the second largest in China market right now for EV, but we think our humanoid market, our humanoid subsidiary is going to be even bigger than EV in the future. So that's his vision he shared with the world. And I do think US, I was in CES 2 weeks ago. We got as much inquiries about humanoid and robotics as much as drones. So I think that's going to be a really interesting market to watch, especially, you don't want to have a nanny robotics and there for like 2 hours and dead, right? You want to make sure that it can last for a longer time, and because the person will likely going to have a very small core. It's not like a vehicle, you have a big base in the bottom. So that's really the challenge we see that's going to coming up with the humanoid robotics as well. The good thing is like battery something is already becoming a fundamental infrastructure for the future of transportation. No matter if it's in a vehicle or it's in a drone or it's in Starlink, right, or it's in the space satellite, right, it's everywhere. So I do believe that it's going to be a really exciting industry, and solid state and sodium-ion is definitely going to be the future.
Yeah, and with respect to humanoid robots, it's a really, just from a perspective, there's the battery angle, which is super interesting, and there's a lot of opportunities. But yeah, who knows where the world will be in 5 or 10 years with respect to that. I would like someone to be doing my cleaning for me if that's possible. Sven, we mentioned in some of our previous conversations about, you mentioned how AI data centers is something that you guys are really focusing on. So you mentioned it in her answer as well. So do you see this as an underappreciated opportunity for solid state batteries, and any other markets that you see as like really good challenges, maybe regionally as well as sort of sectorally?
Well, I would say that Lexi just now mentioned that AIDC. The thing is that in our traditional data center, and the power is about 8 to 10 kilowatt for this computation, and therefore the lead acid was playing the role for the UPS. But when we move to the AI DC center, and with this kind of 800 volt and design architecture, and then this power was boosted to 50 and even to the 200. And this demands, let's say, the high, let's say, power density of the batteries. On the other hand, that because of the conventional, let's say, the UPS rooms, and this kind of design will not be able to, let's say, fulfill all these requirements. And therefore, this new, let's say, battery backup system is called a BBU, and they are put on the shelves. And they require high energy density, high power density, and then next to the GPU and the GPU. And this basically makes, let's say, additional layer of the safety requirements. And we are exploring these territories, and we believe that for the batteries which could, let's say, hold, let's say, high safety standards, and also to have the perform this high power density, there will be big opportunity here. And humanoid is another one. Just now, you also mentioned like XPeng, and basically for this kind of application for the humanoid robotics, there is a key difference and from the conventional one. For example, the programmed one or let's say remote controlled one is that the AI edge computing. Because conventional one will have the robotics and it's programmed, or let's say they have let's say kind of let's say design program for it to practice. But for the AI based one, the difference is that it has to make a decision by itself. There's a large amount of computation behind it. It consumes lots of energy. And on the other hand, that for the AI humanoid, and normally that is living with us and in the rooms, and the safety is very stringent. We are talking with some of these kind of robotic companies, and in China, outside of China, And they were thinking about at first, let's say the safety comes first, and the solid state battery should be the direction. But let's say what kind of solid state battery, and they are hesitating. And we came up with this kind of solution with, let's say, high nickel content, and they even regard, let's say, with high nickel content one will be not safe enough. Yeah. We have to, let's say, use other solutions and to keep the high energy density while to boost its safety standards. Yeah. This is second one. In terms of long term, and for me, I would say the V2G, that will be something very, very unique and at the mass market. But I'm saying so that probably we also hear lots about the demand side flexibility. Because previously I was studying the grid systems. If we think about the grid, the energy transition, and the energy transition is everything about around the grid. And the grid need to be balanced. But we have this the transmission system and also distribution system. And for the distribution network, previously it does not need to take care of the balancing issue. But when we have more and more EV, we have more and more, let's say, household battery and the rooftop PVs, and this kind of balancing under this distribution network, and it becomes very, very challenging. And therefore, we have to use digital tools, different ways to balance it. But for the low voltage distribution network, it is challenging that they can only find, let's say, electricity within this area. But if we have, let's say, the EVs, like this you mentioned, the long cruising distance one, and it has sufficient electricities, it can naturally move among different distribution networks. And this brings, let's say, most ideal, let's say, the flexibility.
And one of the methods of, or one of the benefits of the higher cycle life of maybe some of these technologies is people are more relaxed to do vehicle to grid bidirectional charging, right? And use their EV battery as a sort of stationary home battery.
Exactly. And for me, let's say, in my thinking, that the long durability and also the high energy capacity for the EVs, in the future, it is going to change how we look at the EV. And in the future, the EV will first have its transportation trait. This is conventional. Second one is AI-related, new business model and etc. The third one that will be kind of, let's say, the V2G. Whenever that you park your car, and wherever you park it, it will always connect to grid. And when we move to that stage, the EV will not be a, let's say, productive buy to consume, but it is something that could, let's say, make money for you. Because when you sell the electricity to the grid or charge the electricity from the grid when there are plenty, and you always get, let's say, paid for this one.
Yeah, this is a really good opportunity and something that, your battery technology could enable. Moving on to Tim, so you're working, as you said, with PowerCo, and they have manufacturing sites that they're planning and operating in Europe and in Canada. We heard, unfortunately, in Colin's opening talk this morning in the plenary that BNEF's expectation for the EV market in the US is actually a slight contraction in 2026. But whilst you're based here in Canada, as you said, it's not a good place to do the manufacturing. So the manufacturing is happening maybe in Europe and Canada. Are the opportunities and the growth in the markets there a really strong benefit for you and working with players in other regions in the world?
Yeah. So PowerCo is our publicly announced partner, but we are working with others. So addressable market is larger than that. Transportation is obviously a giant market, $200 billion, growing in the near term to $300 billion. A huge and growing market, and a very important one for climate and other reasons. But also, I think what makes me excited are some of the advanced applications that new batteries are going to enable, some of the ones that Siyu was mentioning. And I'd like to highlight the critical role of safety in a lot of those advanced applications. If you have a battery underneath your $1 million rack of GPUs, or if you have a battery in the car that you're getting into and your family's getting into, or if you have a battery in your phone that if you drop it on the airplane, a flight attendant has to come and retrieve it for you. All of these areas highlight, I think, the critical importance of safety in a battery. A lot of people think that solid state equals safer. It can, but not necessarily the case. There are some solid state batteries that are more safe than others. So I'd encourage people who are interested to dig a little bit more into the details. It's not just as simple as, well, you get rid of a flammable liquid, therefore it's safer. There are some solid state batteries that have gases that react more with moisture. Some solid state batteries have more energy density, so more potential risk there. But our battery is quite safe, and I think one of the key design aspects of our battery is a ceramic that separates anode from cathode. One of the biggest advances in battery safety recently was including a little bit of ceramic particles on the polymer separator, and that is now standard in phone batteries and becoming more standard in EVs. Our separator is fully ceramic, so you get something that if there's a battery safety event, it just becomes a hot rock, not something flammable or combustible. So I do think that that's really important to enabling a lot of advanced applications.
Thank you, Tim. And Landon, coming back to thinking of sodium ion, so data centers, I mean, they were the topic of the whole conversation at the event yesterday for those of us that were there, and it's already come up a few times on this panel. They're a major opportunity for sodium ion, right? Especially given the uptime and maintenance advantages that you've already talked about. Do you think, and I'm sure you hope, but do you think that sodium ion can become the default for certain applications in stationary storage, even if lithium-ion prices continue to fall, as we've observed over the last 10 or 15 years?
Yeah, I mean, I think, to answer the second question there, that it's already happening. We're pretty much sold out for the next 2 years, and we're looking at ways to expand capacity so that we can keep up, especially in 2027 and in out years. So right now it's a math test. Like the passive cooling, the benefit of that basically means that you could give the battery away for free, and you still are better off choosing, give an LFP battery away for free, and you're still better off choosing sodium ion. We're down to that point. Like, go back 3 or 4 years ago, LFP was expensive enough where it was like that, reducing it by a material amount, 10% reduction was a really big number. Now it's so cheap that a 10% reduction is relatively marginal. Now you have to look at everything else around it. In fact, if I was doing the back of the envelope math earlier today, if you just look at like a solar panel and a battery, just the cost of those two things, and you calculate the levelized cost of energy, it's already like 40% the cost of a combined cycle gas turbine. So it's all the stuff around the battery and the solar panel that make it too expensive to be competitive. And it's already pretty close, but the goal is really to get that balance of system stuff and all the other things that go around this so cheap. And I think that becomes really imperative when you get to the second question, data centers, and the broader topic about AI. We're at a pretty important inflection point in history where up until now, it's been calories in, productivity out. Now it's electrons in and increasingly going to be productivity out. And how efficiently we generate, store, and use those electrons is going to become a measure of how productive your entire economy is, how much you can produce and continue to be productive for the long haul. And I think it's really important and gives me hope in some ways too, that if you think about all of us up here, we're talking about pathways to improve a technology that has been on a very fast cost reduction clip over the last 25 years. There's a massive amount of innovation and opportunity space to still explore. So there's no, I'm firmly convicted that you're going to see, at least for the next 10, 20 years, further massive reductions in price. And you can't say the same for existing fossil infrastructure. I mean, that sort of infrastructure is not getting cheaper over time. It's sort of just plugged to how much these molecules cost in the market. And so as we think about AI data center sort of applications, it's really important we pick the right energy infrastructure and invest ahead of that so that we're installing the right generating and storage assets so that we're producing productivity in the future at a competitive rate. And I think sodium ion is our play for data centers very specifically there. We have a single product. It's our grid scale multi-hour solution that goes out in the power yard because you're at higher voltages in these next generation architectures. You can move all of the functionality that are traditionally been done by UPS out there, and now you just have super caps in the rack, substantially less white space inside the building that's dedicated to power, and all your storage goes outside, safer, and a lot cheaper to do it that way. And one of the nice things about sodium is that it doesn't degrade nearly as much with cycling as LFP, so we can handle the really fast cycling that you see in AI workloads. So there's a lot of reason to be very hopeful about sodium, but I think in general the theme that electrification and infrastructure in the grid, upgrading that is becoming a strategically important asset for productivity for our economy, for national security, and whether it's sort of imperative now. It's not optional. We need to be investing in that and accelerating, getting competitive in those spaces.
Yeah, so it does sound like there's a lot to be hopeful for, both for sodium, as you say, but also for solid state. I've got one closing question. If we can just move down the line and try and keep it really snappy so we have a little bit of time for questions in the room. But starting with you, Tim, and not to be too much on the spot, but if we were sitting here in 3 years' time, January 2029, what would have to have happened for you to say, yeah, we have done what we needed to do, we've hit our targets, our batteries are really at where we wanted them to be? What sort of one metric or event or sort of, development?
Yeah, I would look at how many gigafactories are starting to install solid-state battery capacity, and then how many consumer or non-automotive applications are there out in the real world that you can use, whether they're drones or something else.
Thank you. And CE, so what sort of one number or metric would you like to really hit to say, yeah, Factorial have got to where they need to be?
Also, you will see Factorial batteries being used there in the vehicles and also in the air.
In the air as well, yeah. I hope, Landon, for Peak Energy, what is the sort of the marquee event that you'd like to complete in the next 3 years?
The next 3 years, I think we want to be shipping somewhere on the order of like 8 gigawatt hour battery by then, batteries, and then other power infrastructure as well, which we haven't talked publicly about yet, but coming soon.
Okay, interesting, something to keep an eye on. And Sven, so for Heitzer, what would you like to achieve in the next 3 years to say that you're really on the road to commercialization?
I would say maybe broadly speaking, not only to the Heitzer itself, is that the number of the battery-related fire hazards is you can see apparently the drop by using the solid-state battery.
Okay, thank you very much. So that brings to the end of my questions. So thank you very much for coming with us on this conversation. Are there any questions in the room? We've got a few minutes left. If anyone has anything they want to pose to the panelists. Okay. Oh yeah, sorry, I didn't see. So I'm just going to repeat that for the recording. How do you, for the sodium-ion product, how do you balance the energy density versus other metrics?
So for our product, the big penalty we took up front was energy density, and we took that knowing that we had substantial headroom on safety and on degradation use cases. So it was sort of a strategic decision to say, like, look, we know this will be a problem to solve on like cost and energy density, which translates to cost in this application. That's mostly what matters there. But we wanted a lot of headroom on these other things because it can be really technically hard to prove you've solved degradation or safety. It's very expensive too. So we took that way, and a lot of the way that Peak's we're not even 3 years old yet, and to get into gigawatt hour scale. Starting next year, which is really what we're going to be doing, you gotta make these choices where you're like, okay, where do I want to take risk, and where do I want to be conservative? And our strategy as a company has been to sort of push those like unknown unknowns out, which doesn't mean we're not doing them. You have to work on them, but they're going to be a little bit later. They're not on the critical path. And our MVP launch product has to be super competitive in the market, better than anything else out there, but it can't take those unknown risks. So that's where we are today. As we push energy density back up and push other performance metrics up, we have to just make sure we don't break that safety case.
I guess just a sort of maybe follow-up comment or question is, there's the energy density at the cell level, but also if you're doing passive cooling and not having other sort of things going into a containerized solution, that energy density at the container solution is, maybe there's still a deficit. I don't know. You can give me the numbers, but
at the site level, we're about like 15% lower energy density than LFP, but at the cell level, we're about 40%. So you
can make up some of those losses. Any other questions in the room? Yeah, we have one in the center here.
I'll say for the cell level, we're targeting at cost parity at scale with lithium-ion batteries. I mean, sodium-ion, that's a different market. Like in the battery market, we're seeing this bifurcating into two segments. One is more the value segment that's really dominated by LFP today, but I think that's the future for sodium-ion. And there's another segment, it's anywhere like the top 50%. That's really dominated by NMC right now, but it's not good enough. It's not cheap enough. So solid state, we're seeing that in the future, we'll be able to get to that cost parity with lithium-ion battery. But at the system level, like we're able to potentially reduce the total cost of ownership. Because right now, traditional EVs are roughly about anywhere between 500 to 3,000 pounds heavier than combustion engine. If you're thinking about how much weight you're using for like the steel, aluminum, all of the stuff to house the heavy-duty batteries, it's a lot of cost. So if you can have a lighter vehicle, have a smaller pack, and you have a more efficient vehicle, you can have cheaper materials and potentially have even longer range. So that's where we see that the total cost of ownership is similar to the sodium ion. You also have a lower total cost of ownership of the vehicle and also the pack.
What I'd add is that not all solid state is created equal. There's some solid state that use a conventional anode. Some use a lithium metal anode, which is more expensive than conventional. Ours were designed to have no anode. It's an anode-free design where all the lithium comes from the cathode. One reason we did that is because we think that will be a cost advantage. You eliminate the materials and the production process of the anode.
If I may, I just want to add one more sentence, is that thinking about, let's say, the cost and the insurance fees. Yeah, you should think about the overall, let's say, the lifetime of your batteries or your application. If you, let's say, yes, the solid-state battery at the beginning is more expensive, but if you, by owning this kind of, let's say, advanced, safer technology, and you can save from your insurance over the, let's say, 20, 30 years of ownership, that is huge saving.
Right, and to that point, I think China recently announced is one of the leaders in their entire battery space. They said that China, in the past 30 years, they made a right choice between lithium-ion battery versus nickel metal hydride, and they thought that was the right decision. Now it's a $300 billion market for them, and they think the next 30 years is solid state. That's what they want to bet on, just for information.
Yeah. Well, thank you very much for the questions in the room. We've got to time, unfortunately, so yeah, we'll have to draw this to a close, but we talked a little bit about where you guys are at the minute and the inflection of both these two industries. Some of the challenges to overcome, but then, yeah, there's a lot of opportunities, and maybe the next 30 years is all solid-state batteries, as you say, CE.
Sodium-ion too.
And so, well, for different applications. And my personal view is...
complementary to each
I would say
other.
more safer battery.
Yeah, my personal view is there's a very large battery market out there. Lithium-ion isn't going to die away, but I think there's space for sodium. There's a lot of space for sodium and a lot of space for solid-state as well as the market continues to grow year on year. So thank you very much. And yeah, if you can join me in thanking my panelists for this session.